Hey everyone, and welcome to this video on trigonometric functions and their reciprocals. This is the first unit of the trigonometry topic. It's going to be relatively dense. I'm not going to provide too many examples, but hopefully based on the examples that I do give you, you're able to generalize to solve other problems. So in terms of the unit outline for this unit, essentially what we're doing is we're solving trigonometric equations with transformations, with like various levels of complexity of transformations. We're then going to be having a look at graphing trigonometric functions that have several different transformations applied to them, and this is to a more complex degree than you deal with in methods, obviously, because this is specialist. So you can deal with up to 4 different transformations, namely these being, in this case it's not included, but you have your horizontal dilation here with A, your horizontal translation with B, which generally in trigonometry is referred to as a phase shift, and then you've got your vertical translation C, where you move up and down, and then something that's not included here is the vertical dilation, but that would essentially slot in just before that function there, and that affects sort of the amplitude of the function. Then finally, you're dealing with reciprocal trigonometric functions. So you're going to deal with cosec of an angle, the secant of an angle, and the cotangent of an angle. And those are defined as the reciprocal trigonometric functions of sine, cosine, and tangent, respectively. And then we're going to be graphing them and sketching a couple of simple transformations of them as well. And that'll take us to the end of this video. It is quite dense. And I would say trigonometry can be one of the harder units, but once you start grasping it and doing a bit of practice, I think it becomes quite fluid and straightforward. So let's just get straight into the video then. Okay, so the first thing I'm going to do is I'm going to go over solving trigonometric equations of this form, which is trigonometric equations where the trigonometric function has a set of transformations applied to it. And more specifically, I'm looking at sort of basic trigonometric functions, which are sine, cosine, and tangent. Now, before I go into that, I just want to go over some exact values that we know of. To remember the exact values that I'm talking about, what I was taught were these things called the God triangles. This first one is essentially an equilateral triangle with side lengths of 2 that's been sliced in half. And so as a result, you have 1 here because it's sliced in half there, and root 3. And so because it's an equilateral triangle, this is 60 degrees, this is 30 degrees, and this is 90 degrees. Now the other one is an isosceles triangle, where this is 45 degrees, that's your right angle, and root 2. And because the base angles, the sides are equal, the base angles are equal. So these are the 2 God triangles that help us remember 30 degrees, 45 degrees, 60 degrees, 90 degrees, 0 degrees, etc. And so if we remember SOHCAHTOA, we have SOHCAHTOA. Remember that sine is equal to opposite over hypotenuse. So in the case of sine 30 degrees, that'll be 1 divided by 2. So sine 30 degrees is 1/2. Cosine is adjacent over hypotenuse. So if we're looking at 45 degrees, that would be 1 over root 2. So cosine of 45 degrees is 1 over root 2. And then tangent, we have opposite over adjacent. So let's say we're looking at 60 degrees. Tan of 60 degrees is root 3 over 1. All right. Now, the other thing that we need to go over is radians and degrees. And these are essentially 2 ways of measuring angles. And generally, the conversion here is that pi radians is equivalent to 180 degrees. And so that allows us to draw a bunch of other relationships, like pi on 2 is equivalent to 90 degrees. Pi on 3 is 60 degrees. Pi on 4 is 45 degrees. And pi on 6 is 30 degrees, sorry. Okay, so these are some important radian angles that we need to memorize because they correspond to the exact values that we know. Now, when we're dealing with a function, like let's say we're trying to solve the values for x for which cosine x is equal to 1/2. All right. This equation by itself has infinite solutions, and the reason why it has infinite solutions is due to a concept referred to as periodicity. So when it comes to periodicity, here we have, for example, cosine 1/2 might be over here. And more specifically, cosine 1/2 is specifically when x equals 60 degrees here. So you've got your 60 degrees here. Then you've also got, if we go around, due to the symmetry of sort of cosine always refers to the x coordinate, so down here. So if we're looking here, down here, then these both correspond to the same cosine value. So that's 60 degrees, and the other one is 300 degrees if we rotate around in an anti-clockwise direction from the positive x-axis. And then if we go around another period, then we go to 360 degrees plus 60 degrees, and that equally is equal to the same value of 1/2. And so essentially what we can do is we can keep going around and around and around this unit circle and keep getting these values of 1/2. And so generally when we're solving a trigonometric equation, we generally restrict bounds. We put some bounds onto this function, so we only get 1, 2, 3, 4, or 5 maybe sort of values. Very common one is maybe we go from between 0 and 2 pi. And another way of representing this is with square brackets, 0, 2 pi. What the square brackets represents is less than or equal to or greater than or equal to. So essentially what the square bracket represents is that the x can be equal to 0 and greater than 0. If I used a rounded bracket like this, that would mean it does not include 0. So if we have, for example, 0, 2 pi like this, that would correspond to 0x 2 pi, not including the 0 and the 2 pi within those bounds. So if we're trying to solve this, cosine x is equal to 1/2. If we look at our unit circle and we look at our God triangles, we're looking here, 60 degrees is equal to 1/2. So x will be equal to 60 degrees, but because it's in radians, we need to represent that as pi on 3. Now that's up here, approximately. The other one is symmetrically downwards, which is negative pi on 3 in this direction. However, we can't do negative pi on 3 because our bounds are 0 up to 2 pi. So instead, the way we have to represent it is in this direction, which in this case is equal to 5 pi on 3. Now, if we do cos x is equal to 1/2 restricted for negative pi up to pi, then in this case, it would be equal to negative pi on 3 and pi on 3 based on those bounds. And this negative pi on 3 here would kind of coincide with the 5 pi on 3, except they're one period apart. So that's the concept of periodicity there. Now, the next thing I'm going to go over is these transformations. So we have a function, maybe a f b x plus c plus d is equal to e. So I've made this slightly more complex than the example that's given in 2.1.1, and that's because you actually can get a lot more transformations than you think. And so what I'm going to do now is I'm just going to break down what each of these variables do. So what this a does is it affects the amplitude. More specifically, it only affects the amplitude of sine and cosine because these are the only trigonometric functions that have an amplitude associated with them. So amplitude is essentially defined as the maximum displacement of a function away from the positive x-axis. So if we've got sine here, for example, the maximum amplitude is something like this or something like this here, and that's our maximum amplitude away. And similarly for cosine, we might have something like that, and our maximum amplitude is represented by this here. Okay? All right. So that's sine and cosine. Now, it doesn't, there's no definition of amplitude for tangent. So for tangent, if we look at the function, it looks something like this, right? And so there's no sort of amplitude equation because essentially it goes from negative infinity up to infinity. So the concept of amplitude doesn't exist for tangent. This is also importantly distinct from a vertical dilation. Vertical dilation refers to multiplying everything by a constant. So a vertical dilation would be something like this. In this case, the a only refers to the trigonometric function rather than the entire function. If we didn't have a d, if this didn't exist, then a would correspond to a vertical dilation. So if I just have a, f of x, fb x plus c, in this case, a would be both a transformation to the amplitude and also correspond to a vertical dilation by a factor of a. Now the second bit here is the it affects the period of the function, and the period is essentially defined as how long it takes for the function to repeat itself. Okay, just going to remove these brackets. Okay, period. How long a function takes to repeat itself. A trigonometric function takes to repeat itself. For sine and cosine, that's 2 pi. And for tangent, that's pi. Now the period is defined as, according to this transformation, for sine and cosine, it will be equal to 2 pi over b. And for tangent, it'll be pi over b. So if we have a b value, some sort of b value, it's going to affect the period by a factor of 1 over b, which is kind of the opposite direction you'd kind of expect it to, and it's the opposite to how a affects the function, for example. This next one here affects the horizontal translation, which in the context of trigonometry is generally referred to as a phase shift. Okay, so again, just like b, it kind of affects it in the opposite direction. If we have x take pi on 4 in this case, for example, that corresponds to a shift to the right, while normally we associate negative to a shift to the left, but it induces a shift to the right. And x plus pi on 4, that induces a shift to the left, okay, of pi on 4 units, assuming that b is equal to 1. Now finally, this is our vertical translation, and what this affects is the location of the midline. And what I mean by the midline of a trigonometric function is if I have got a function like this, then the midline is the line around which it oscillates. So if I shift it up this much, this represents my value d. Okay, so it is a vertical translation of my trigonometric function. All right, cool. So that's all of that. Now let's get an example of where we might need to solve a transformed trigonometric function. So let's say we have 2 cosine 2x plus pi on 4 is equal to root 3. Okay, and my bounds are 0 up to 2 pi, inclusive. When we have a trigonometric function like this and we have something within these brackets that make it slightly more complex, the very first step that we want to do is adjust the bounds to reflect that. To adjust the bounds to reflect it, essentially what we do is we plug in each of these bounds into this equation here, or more specifically here, to see the adjusted bounds. So if we're plugging in a 0 here into x is equal to 0, 0 plus pi on 4 is equal to pi on 4, and pi on 4 times 2 is pi on 2. So we have our pi on 2, and then we have 2x plus pi on 4 because we've adjusted it. And then if we plug in a 2 pi, that's 2 pi plus pi on 4 is 9 pi on 4, times 2 is 9 pi on 2. Okay? And then we can divide by 2, so we get cos 2x plus pi on 4 is equal to root 3 over 2. All right? So that's our adjusted bounds. Now, the next thing we want to do is we want to solve for whatever's in this. We don't need to really worry about that now. We can, for all we care, we can call that y. Like this bit, we can just call that y. So we're basically solving cos y is equal to root 3 on 2, where we've got pi on 2, y, 9 pi on 2. That's another way we can kind of think of it, but I'm not going to do that. So root 3 on 2. Root 3 on 2, based on our God triangle here, root 3 on 2 occurs when x is equal to 30 degrees, or pi on 6 radians. However, if we're looking at our period, we've got it restricted from pi on 2 onwards. Pi on 6 is not as great as pi on 2, so it doesn't meet our lower bounds. The next value at which it is equal to root 3 on 2 is at 11 pi on 6. So our first solution in this case is 2x plus pi on 4. That'll be equal to 11 pi on 6. The next case is moving along again to 13 pi on 6 on our unit circle. And then we can go around another period. So 2 pi plus 11 pi on 6. That gets us to 23 pi on 6. And then this next one, we have 13 pi on 6, and we can go around one more time, and we can get to 25 pi on 6. And now this is still within the bounds of 9 pi on 2, because 9 pi on 2 is essentially 4.5 pi. So that's essentially 2 rotations plus another half rotation. And this is within those bounds, because what that represents is 2 rotations and then pi on 6. Whereas this is 2 rotations and then pi on 2. So that's still within the bounds. So these are our 4 solutions. But the thing is, what we want to do, we don't want to solve for 2x plus pi on 4. We want to solve for x. And so to do that, we get to x plus pi on 4. And what that's equal to is 11 pi on 12, dividing by 2. We have 13 pi on 12. Don't know why this has suddenly gone so thick. 23 pi on 12 and 25 pi on 12. Okay? And then once we've done that, we want to subtract out our pi on 4. And so we get 8 pi on 12. We get 10 pi on 12. This is by subtracting pi on 4 from each of those values. We get 20 pi on 12. And we get 22 pi on 12. Okay? And we can simplify those. We can get, for instance, here we can get 2 pi on 3. Here we can get 5 pi on 6 if we wanted to simplify. Here we can get 10 pi on 6, 5 pi on 3. And here we can get 11 pi on 6. Okay? And so this is essentially the process. You don't necessarily need to understand why you do this adjustment to the bounds, but essentially that's a mathematical process that works. You can maybe think about it a little bit to see how that works, but it's more important that you're able to, in ATAR at least, it's more important that you manage to get the right working and come to the final answer. And so this is the process, and there'll be a lot more questions that you can kind of tackle in the Sadler textbooks and in the OT Lee and in the Nelson textbooks. If you think that this has gone too quickly, make sure that you ask me a question in the comments. Maybe you want to schedule a tutoring session, face-to-face, an online tutoring session. But anyway, regardless, leave comments if there's anything I can do to improve this. And I think there's one comment that I received not too long ago about maybe releasing a longer video where I go over working for exam questions. And that's something I'm going to be working on once I've finished the Year 11 Methods, Spec and Chemistry courses. So thank you for recommending that. And that's something hopefully that'll come up a bit later this year for you guys. Anyway, so that's that first 2.1.1 finished. So on to the next. For this next component, I'm going to go over graphing examples of sort of transformed trigonometric functions. And I'm going to go over, hopefully, 2 cases. I'm going to go over a sine case and I'm going to go over a cosine case, a sine case and a tangent case. And I'm also going to look at sort of what the relationship between sine and cosine is. And I think that's what I'm going to do first, actually. So if I look at my sine graph like this, and I can kind of extrapolate it to back here, what a sine graph kind of looks like is something like this. And it also extends back in this direction and goes on and on and on. If I look at a cosine graph, okay, it looks kind of like this. Okay, and that kind of keeps going on and on and on. Okay, so one of the things that I notice here is if this is just a normal y equals sine x graph, y equals sine x, and this is a normal y equals cos x, this is a y equals sine x, then this kind of corresponds to your pi on 2, right? If I kind of look at that, if I look at this kind of component of my function here, essentially what that is it's this component here, right? This component here shifted pi on 2 units to the right. Okay, so essentially what sine x is equal to is cos x, but shifted pi on 2 units to the right. Okay, alternatively, sine x, cos x is sine x shifted pi on 2 units to the left. So if I shifted this back, then I would get cos x. Okay, so that's kind of the relationship between sine and cosine. They're essentially a phase shift of pi on 2 units away from each other. They're just out of sync. Okay, now I've got that out of the way. I want to go over sort of what how to graph transformed trigonometric functions. Like for example, let's say we want to graph 2 sine 2x plus pi on 4 like this plus 3. All right. In this case, we always need to consider the order of operations. The first thing that occurs to x is it gets shifted pi on 4 units to the left. So if we're looking at our normal sine function like this, okay, we have our normal sine function like this. What's happened here is I've shifted pi on 4 units to the left. Okay, so if I look at my renewed function like this, essentially what's happened is pi on 4, it's been shifted back like that. And so this now starts at negative pi on 4. This is at the point pi on 4. This, which was previously at pi, is now at pi minus pi on 4, which is 3 pi on 4. This point here, which was previously at 3 pi on 2, is now at 5 pi on 4. And this point, which was previously at 2 pi, is now been shifted pi on 4 units to the left to 7 pi on 4. Okay. Now, the next thing that's occurred is that I have experienced this horizontal dilation by a factor of 2. So essentially now what's happened is all of my sort of factors here have been squeezed inwards towards in this direction by a factor of 2. So essentially what this 2 does, if it's greater than 1, is it starts squeezing things inwards. Everything gets divided by 2. So in this case, if I was to graph that function then, if I have this looking something like this, then now this is at negative pi on 8. This is at pi on 8. This is at 3 pi on 8. This is at 5 pi on 8. This is at 7 pi on 8. Okay? So that's what's happened now. Now the next thing is, usually for this amplitude, we're at 1, right? We're at 1. We've got an amplitude of 1 for the normal sine function. But in this case, what's happened is we've increased our amplitude to 2. So now I'm at 2 here, and I'm going down to negative 2. So our amplitude has been affected. Now the last thing that's happened is I've had this plus 3. That means my midline, which was previously at 0, has now shifted up to 3. So my midline now is at 3, and as a result, I oscillate up to 5 and down to 1. And so if I look at my function, my trigonometric function, it looks something like this. And these values correspond here. This corresponds to pi on 8. This here corresponds to negative pi on 8. All right. This corresponds to 3 pi on 8. This corresponds to 5 pi on 8. This corresponds to 7 pi on 8. And so this point here is 3. So we go up to 5 in this case and down to 1. And so this is a transformed graph of sine according to all of these transformations. Now this is a really complex case. This is probably the most complex case you'll get. And generally when you're graphing functions like this, you're going to need to graph them according to a set of bounds. So maybe they say graph this function for 0 up to 2 pi. So for 0x to 2 pi. And in that case, you just need to graph it all out, a really long sine function, and then gradually add on these transformations. And the really key important thing when you're doing this is thinking about the order of operations. So for example, 2x plus pi on 4, in this case, within the brackets, is different to 2x plus pi on 4. If you have 2x plus pi on 4, the order of operations is first you do this horizontal horizontal dilation by a factor of 1/2, and then you do this translation or phase shift of pi on 4 units to the left. So the order of operations matters. All right. Now let's say we have a tangent graph, and I'm going to go over a slightly easier example here. Let's say we're looking at graphing something like y is equal to tan x plus pi on 3, or actually let's make it minus in this case, minus pi on, let's make it 2 plus 3. All right, so if we have our normal tan function, it looks something like this. We go up to infinity, we go down, around, and back up to infinity like this, and so on and so forth. And if we look at our unit circle, we know that the infinity occurs when, in this case, it's at pi on 2 or 90 degrees. Here it's at 3 pi on 2, and tan is equal to 0 at pi, okay? Another thing is that it equals 1 at the point pi on 4. That's a really key other point. So the key kind of points you want to knock off when you're drawing the graph in this case is that it passes through 0, that your asymptotes are at pi on 2 and 3 pi on 2. And this should go to 2 pi. Okay, your asymptotes are at pi on 2 and 3 pi on 2, and you pass through 0 at the point 0 pi and 2 pi. Okay, so this is 2 periods of tan, because see, you can see that it repeats. That's 1 repetition, and that's the second repetition. Okay, now the next thing that we do is what's happened here is I've shifted pi on 2 units to the right. So remember, our order of operations matters. The first thing that's happened is we've had a phase shift of pi on 2 units to the right. So this is my y, this is my x. And so if I've shifted pi on 2 units to the right, it kind of looks like this and this, and so on and so forth. So if I have these dots here correspond to this point here, because that's all been shifted over. And so now this is at pi on 2, this is at pi, this is at 3 pi on 2, and this is the next asymptote at 2 pi. Okay? And so then if we extend that out, it kind of looks like that. The 2 pi that was here is now at a 5 pi on 2. Okay? And so that's that first transformation. That's that phase shift. Now the next thing is that we've shifted everything up 3 units. Okay? So in this case here, if we're looking at that, then it kind of looks like here. All right, that goes down there, and then we go here and there again. So these points here essentially correspond to 3, okay? This is at pi on 2, this is at pi, this is at 3 pi on 2, this is at 2 pi. This is our asymptote, okay? Now another key thing is that pi on 4 corresponds to 1, but the pi on 4 is now at 3 pi on 4, because we've shifted pi on 2 units towards the right. And so this point here, that used to correspond to the point 1 from the midline of 0, but now that has to correspond to a point of 4. Okay? If we remember from our God triangle 1, 1, root 2, we have 45 degrees here, or pi on 4. And tan 45 degrees is 1 over 1, or 1. Okay? And so that also corresponds to this point here, which in this case is 7 pi on 4. And equally on either side, this corresponds to kind of a -1 value, 2. That's our, in this case, 5 pi on 4. Okay? So if we're looking at like kind of the negative side of, based on the symmetry of the unit circle, if we have pi on 4 over here, negative pi on 4 corresponds to a -1 value. So pi on 4 on either side of this kind of 0 point correspond to 1 and -1. 1 and -1 on either side. And so this is kind of the transformed y tan function with a phase shift of pi on 2 units to the right and a vertical translation of 3 units up. Okay? This is really, I would say this is one of the more complex things to wrap your head around when you're starting off, but once you get the gist of what's actually happening, it becomes really, really easy. Obviously, if you get the gist of what's going on, then it's easy. So yeah, you've got your sine, you've got your tan graphs that I've given examples of here. Cool. So moving on to the last point here, which is reciprocal trigonometric functions. So when it comes to reciprocal trigonometric functions, the way that they're defined is we have 3 of them. We have cosecant of x, which we sometimes express as CSC of x. We have secant of x, and we have cotangent of x. And cosecant of x is equal to 1 over sine x. Secant of x is equal to 1 over cosine of x. And cotangent is equal to 1 over tan of x. Okay? So if I'm looking at cosecant of x, the easiest way to graph any of these reciprocal functions is to first of all graph the basic trigonometric function. In this case, this is y equals sine x. Now, if we're doing 1 over sine x, that means any time I pass through this point 0, I'm going to have an asymptote because I can't divide 1 by 0. So I have these asymptotes here. And let's say I'm going to graph my reciprocal function in yellow. So I have asymptote here, and I have another asymptote here. Okay? And here is the point where sine is equal to 1. And 1 divided by 1 is 1. So cosecant x is going to equal 1 at this point here, which in sine x is pi on 2. This is 3 pi on 2. This is pi, and this is 2 pi. Okay? And at 3 pi on 2, sine x is equal to -1, and 1 divided by -1 is -1. Now, as I progress down here, my sine value becomes steadily and steadily smaller and approaches 0. If I'm dividing 1 by a steadily smaller and smaller number, I'm going to get a larger and larger number. So as sine decreases, cosecant of sine increases, and it looks something like this. Similarly, as I become a slightly smaller and smaller negative number, as I approach 0, I'm going to become a really large negative number. And as a result, I approach infinity on either side like this. And so this is in the yellow, is a graph of y equals cosecant of x. Now, if I look at cosine, I have my cosine, it looks kind of like this. And similarly here, I'm going to have, maybe I should just draw this a little bit smaller. Okay, here I have 2 points where it passes through 0, and I go up along this way, down along this way, up along this way, down along this way, okay? And so at 0 it passes, we have asymptotes because you can't divide by 1 by 0. Here, 1 corresponds to 1, 1 divided by 1 is 1, 1 divided by -1 is 1, 1 divided by 1 is 1. Now as my cosine decreases and becomes a smaller and smaller number on that side, my secant of x is going to start tending towards infinity. And here, as I go towards 0 on either side here, my secant of x is going to tend towards negative infinity on either side. Okay? And here, similarly, as it goes down towards 0, 1 divided by a steadily smaller and smaller number starts tending towards infinity. And so this here is a graph of y equals secant of x. Finally, let's take a look at tan. So tan kind of looks like this, something like this. And this is for a period of 2 pi. So I've got essentially 2 periods of tan. Now, in this case, this is a bit of an interesting case because here we have some asymptotes where we're tending towards infinity. And so for my cotangent of x, 1 divided by infinity is going to pass through 0. And these 0 points are going to be my asymptotes. Asymptote here, and finally an asymptote here, right? And so on this side here, I've got infinity and I'm approaching 0 down here. So as I approach 0, I get smaller and smaller. 1 divided by a smaller and smaller number is going to tend upwards to infinity. And similarly here, it's going to tend downwards to negative infinity, upwards to infinity, downwards to negative infinity. Now remember, at pi on 4, tan is going to be equal to 1. So this point here is 1. So cotangent of pi on 4 is also 1. This is 1, this is negative 1, negative 1. That negative 1 there corresponds to 3 pi on 4 on my unit circle. Here, tan is equal to negative 1. And 1 divided by negative 1 is negative 1. So if the black is tangent, the yellow in this case is y equals cotangent of x. And it kind of looks like a weirdly flipped around tan graph a little bit, right? Okay, last thing I'm going to do is sketch some simple transformations of reciprocal trigonometric functions. Again, the easiest thing to do is first to graph the basic function, that is sine, cosine, or tangent. So I'm going to graph, let's say I want to graph the equation of 2 secant x plus pi on 4. All right. Cool. So when I'm doing this, anything within the brackets, this is my tip for you. Anything within the brackets, it's easier to just apply that transformation to the basic function. In this case, that corresponds to cosine. So one of the things I should mention is cosec, sec, and cotangent. The third letter corresponds to the basic trigonometric function it corresponds to. Cot responds to tangent, sec responds to cosine, and cosec corresponds to sine. Okay, that's just a useful memory tool. So returning back to this, within the brackets, it's easiest to apply the transformation to the basic trigonometric function. So in this case, if I'm looking at my function like this, and I have my cosine function like that, okay, it's easier to first apply this pi on 4 transformation to the cosine. So if this is my initial function, I would be shifting everything back pi on 4 units. So this corresponds to negative pi on 4. This corresponds to pi on 4. This corresponds to 3 pi on 4. Yep. This corresponds to 7 pi on 4. 5 pi on 4. All right. Now, once I've graphed that, I can get my my secant sort of graph. So I've got my function like this. My secant graph is going to correspond to asymptotes here and another asymptote here. And that is going to correspond here to that point there going upwards, this point here going down this way, and this way. Okay? Now I've got the 2 in the front. what that's going to do is it's going to cause a vertical dilation. What was previously at 1 is now going to go up to 2, dilated up. Everything essentially gets stretched outwards by a factor of 2. So if my initial function here looked something like this, and I have my asymptote at pi on 4, and 5 pi on 4, and it looks something like this. Oh. So this corresponds to a point 1. This corresponds to a point -1. With the factor of 2 dilation, this is essentially going to get pushed up to here and get even steeper. This is going to get pushed down to -2 and get even steeper as well. And this is going to get pushed up to 2 and get steep too. Okay? So that's this point at 2. Okay? And this corresponds to -2. And so we still have the same asymptotes because there's no effect on the asymptotes. It's just in the vertical direction, everything gets stretched outwards. Okay? So the first thing that we do, anything within the brackets, we apply to the corresponding basic function. And then the 2 is essentially what we apply to the reciprocal function. Okay, last example is let's take a look at y equals cotangent of x plus pi on 2. If we look at our tan graph, it normally looks like this. Easiest thing, it's within the brackets, so we apply that transformation to the tan graph. Applying it to the tan graph, what's happening is we're essentially shifting pi on 2 units to the left. So if we look at this, everything's been shifted over, and what our tan graph ends up looking like is something like this. Okay, everything's been shifted over. So if we look at cot, the corresponding cot, it's going to look something like this. Oh, something like this. This is going to be 0 here. That goes down like that. And this here goes down to 0. Okay? And so that's what our transformed cot function kind of looks like on a graph. If any of this doesn't make sense and you want to book a tutoring session for me to explain this a little bit further, make sure you just let me know in the comments. You can find me on Facebook and organize a tutoring session that way. Otherwise, you can leave any questions you have in the comments section and I'll try to address them in some supplementary content. All right, that is all for today though. We've covered, in this video, we have covered solving trigonometric equations with transformations applied to them. We've kind of also looked at radians and degrees as angles, and we've introduced the God triangles. All of that, the radians, degrees, God triangles, is a bit of a revision of stuff that you've already covered in methods, hopefully. So that stuff shouldn't be too difficult. The only difference between spec and methods is that spec goes into more complex transformations and more complex solving of sort of these transformed trigonometric functions. The next thing that we did was we graphed sine, cosine, and tangent functions with transformations. Again, it's basically the same as methods, but you deal with more transformations layered on top of each other, which can become a lot more complex to graph. And finally, we looked at reciprocal trigonometric functions, what they're kind of defined as. We kind of looked at the third letter corresponding to the basic function that it corresponds to. So sec corresponds to cosine, cot corresponds to tan, and so on and so forth. We also sketched their graphs, and we also graphed simple transformations of them. Okay, this is quite a long video, I'm realizing now. We have gone over a lot of content, and I would say trigonometry is probably one of the harder topics from the year 11 spec course. So if you do need a reviser, make sure you take it slow through this video. And if you need to ask any other questions, make sure you just post that in the comment section, or you can book a tutoring session with me. All right, that's all for today though. Thank you.